In our last video, at the very end of things, we had developed the idea that what we were looking at was the canonical partition function, the uppercase Q, right? And we did some things there where we took the two-level model system and used it to prove that we could, in fact, calculate things about, say, the internal energy and the heat capacity of our system by doing various bits of work with our partition function. Okay. At the end of that video, I mentioned that we could also develop a molecular partition function, which we could assemble by thinking about a single molecule and its available quantum states. And in this video, we're going to begin the process of assembling the terms we need to build that molecular partition function. So my molecular partition function gets the symbol lowercase q, right? It's still a Q. The lowercase q delineates between which one we're talking about. The good news is just about everything about how we're going to calculate these and work with them is the same, no matter which Q I've got in hand. Okay, so there's some differences in the formalism and all and the definitions, but most of the nuts and bolts that you're going to work with are the same in either case. I get my definitions down here, so I can say that my partition function is defined this way. The sum for all the quantum states of e to the minus the energy of the state over kT, right? I've got a second version of the equation over here, which is somewhat different. Those two equations side by side might bother you because they look like I've added a term and not changed anything else. And yet I still say they're both equal to Q. Right. The difference is in the disclaimers down here, essentially. This one, I'm summing over energy levels and including degeneracy. Here, I'm summing over individual quantum states. An example of that would be if I took, suppose I had rotational states and I was at j equals 1, where the degeneracy is 3. I have 1, 2, 3 different energy states that are all at the same energy, right? If I take that and sum over quantum states for that set of 3, I'm going to get 3 terms. They're all going to be identical at e to the minus the energy of those states over kT, right? If I do this summing over the energy level, then I'm going to get 1 term, but my term is going to be the thing that each of the 3 terms was equal to multiplied by the degeneracy, and the degeneracy is going to be 3. So you should be able to realize that those two summations will come out to the same value, right? It is a little bit confusing, the distinction again between quantum states and energy levels, so make sure that you're staying on top of how those differ. In my consideration of the quantum states for my molecule, I'm going to have to think about an array of different kinds of states, right? I'm going to have to account for translational motion. That's the center of mass motion of the molecule, my molecule just flying around in space, right? We're going to start off doing that in 1 dimension, and then we'll generalize to 3 before we finish up in this video. Later, we'll take up rotational motion, then vibrational motion, and electronic states, right? As we go through that hierarchy from translation to rotation to vibration to electronic states, when we do that, we're constantly going to bigger and bigger gaps in the energy levels, right? And so the direction there of that list starts with the term that's going to be the dominant one in the partition function. That translational motion is going to give me by far the largest contribution, then rotation, then vibration, then electronic states, okay? We're going to have a lot more than 2 states, and so we're not really going to want to find our summations by just summing up all the terms, right? So we're going to have to be a little bit more clever and do some math in order to get to our partition functions. Before we do that, I want to talk a little bit about the temperature dependence of the heat capacity, because it's a good lead-in to how this is going to play out. Right? Each mode, each type of motion that our molecule has can carry a maximum energy of 1/2 kT. That's something called the equipartition of energy. Okay. The contributions, the relative importance of those contributions for the different types of states will depend on the temperature, because the populations shift about. Right? If I go to very low temperatures, for example, the vibrational states, pretty much all the molecules will get pushed down into the lowest vibrational state. We've mentioned before, that's what happens at room temperature, right? And in those conditions, those states won't really be contributing. Right? The reason why the translation, rotation, vibration are going to behave differently is because, again, that separation, the spacing between their energy levels is very different from one of those categories to the next. We can see that if we look at the way the heat capacity changes with temperature. So this plot, as it says on the bottom there, is heat capacity on the x-axis, C sub V in joules per mole per Kelvin. On the y-axis, it's got temperature. It's got temperature on a logarithmic scale, right? So the temperatures go from 10 all the way up to 10,000 in this graph. So it's not quite as simple as it looks, right? That's stretched out over a much wider range of temperatures, but it makes it nicer to look at this way. Start at very low temperature, okay? At low temperature, meaning in this case, anything below 50 Kelvin looks like it's low temperature. Sounds like low temperature to me, right? Down there, my graph is labeled to say the heat capacity seems to be flat, and it's equal to 3/2 R. That 3/2 R corresponds to the heat capacity of a monatomic ideal gas. Right? In this case, it's a diatomic molecule, but that's still the heat capacity down there because the only motion that my molecule has right now is translation. Right? It's so cold that none of the rotational states or vibrational states are excited. Right? And so I'm in the ground state for rotation and vibration. I just have translational states populated. 3/2 R is then the expected heat capacity, and that's what we actually see if we measure these. When I get to somewhere between 50 to 100 Kelvin, by 100 Kelvin, my curve is starting to bend upwards, right? Keep going, and by somewhere around room temperature, I've reached a new plateau at 5/2 R. That corresponds to translation and rotation, right? I got 3/2 R for translation because I have 3 degrees of freedom there, 1 for each direction. Right? For rotation, my diatomic molecule has 2 rotational degrees of freedom because it's got 2 axes about which it can rotate. Right? Remember, the third axis is the one that would be the line of centers, and there's no moment of inertia on that, so that rotation doesn't actually count. If I keep raising the temperature, when I get past about 500 Kelvin or so, somewhere in here, I get another upward curve, and eventually my next plateau will come at 7/2 R. That's when the vibrational states are really contributing, right? Vibration's a little different. There's only one vibrational mode, but it contributes R rather than 1/2 R. That's because the vibrational motion has both a potential energy and a kinetic energy piece associated with it, right? Because the atoms are actually moving, and there's also potential energy in the spring-like nature of the bond, right? So if I take this, imagine going down in temperature. As I go down in temperature, what we typically say is that the different degrees of freedom will freeze out at different points. So starting from high temperature, in this graph, I never got high enough to excite electronic states, really, right? Because I don't have those showing up at all. But as I start from the 10,000 Kelvin end of things, I start cooling and I freeze out the vibrations first somewhere so that by 500 or 600 Kelvin, that's all over with. And I'm back on the second plateau, cool farther, and eventually I start freezing out the rotation, right? So at very low temperatures, I'm left with only the translation. To freeze those out of my heat capacity, I'd have to get cooled down to very close to 0 Kelvin, right? Because that spacing of the translational energy levels is very, very small. In this chart, what I've done is I've put together just some estimates of the energies and the energy spacings associated with the different kinds of motion and how those are going to influence their importance to the partition functions. If we look starting with translation, let's look, I guess, in this column here where I've labeled some models, right? The first 3 of those, translation, I've got the particle in a box, rotation, I've got the rigid rotor, vibration, the harmonic oscillator. Those are all things we've talked about in class so far, right? So those are fresh in your mind. For electronic states, we didn't really have a good universal model for that. What I've done is I've used the Rydberg equation, which we have not talked about, and in fact, we really won't talk about. You may have seen that in Gen Chem to talk about justify the wavelengths of light that can be emitted by excited hydrogen atoms. It often shows up in that context in Gen Chem books. But that's just an equation to let us calculate the energy for an electronic transition, okay? I've got over here an estimate of the energies, what we might just think of as delta E, the energy spacing. The energy and the energy spacing are typically same order of magnitude, and this is certainly only good to an order of magnitude kind of idea. I've picked throughout here a 10 AMU molecule, just for the sake of argument, right? For my translation, I need to pick a box length to get the energy, and I've picked 1 millimeter, so I've kept the box pretty small, right? When I do that, my energy corresponds to about 10 to the minus 37 in joules. That's 10 to the minus 15 in wave numbers. The wave number to joule conversion factor is down here. A handy number to have at your disposal is that around room temperature, KT is about 200 wave numbers, okay? So at room temperature, that says KT is very, very much bigger than this 10 to the minus 15 wave numbers, right? So I'm going to have a really lot of translational states that are occupied. That's also reflected in the fact that if I look at this exponential expression over here, that's going to tell me what the importance of these terms are, right? So this says e to the minus delta E over KT. At this point, delta E is very, very much smaller than KT, so this exponential is essentially 1, right? The exponent is essentially 0. Go to rotation. I get my 10 AMU molecule. I had to give it a bond length. I picked 100 picometers. That gives me an energy corresponding to about 5 wave numbers. 5 is still substantially less than 200, and so my exponent is still quite small. My exponential piece is still about 1, and that means I'm going to have a bunch of rotational states populated. Excuse me. Vibrational states, I've still got 10 AMUs. I had to pick a force constant now, and I picked 400 newtons per meter, because that's like at least the right order of magnitude. That gives me an energy that corresponds to 500 wave numbers. Now my energy, my delta E, is bigger than KT, so that flips what happens in the exponent, right? The exponent is no longer close to 0, and so when I do that one, my exponential piece is small. That says a significant majority of my molecules will be in the ground vibrational state, right? So my vibrational states will not be very important in the partition function because they're not very much excited. My electronic states, now my delta E is enormously bigger than KT, right? So now I've got e to the minus, 100,000 over 200 or something like that. So I've got e to the minus 1,000th power, give or take, and that's going to be basically 0, right? That says I have really no noticeable number of molecules that are excited electronically at room temperature, which is what you'd expect if you just think about, you know what you know about electronic states and electronic spectra. All right, so that tells us the translational piece is probably the most important. So that's where we're going to start. My partition function expression just looks like this, right? It says take the summation over all the quantum states, e to the minus e, the energy piece over KT. For my particle in a box, my energies are given by this expression, right? N is the quantum number. So I'm going to take this, and I'm going to stick it in there for my epsilon sub I piece, right? When I do that, I'm now making the summation over all the quantum numbers, right? The quantum number goes from 1, and in principle, it could go up to be infinitely big, right? And when I take that in, I just put that stuff up there where the epsilon is in my exponent, and that gives me this expression there. Right? So that's the summation that I would want to evaluate. That summation is not simple to evaluate, and we're going to have lots and lots of terms, so we're not going to try and just sum them all. Right? What we're going to do is we're going to say, because there are a lot of states populated, and because these quantum states, the energies are very close together, that says I'm going to be able to pretty much replace my summation with an integral. There's a bit of approximation there, but it's a pretty good approximation. Right? And we'll see that when we see how many states are actually occupied, right? So I'm going to transfer my summation, and I'm going to make it an integral. This is a little bit like when you first learn to do integrals, and you say, well, I can approximate the area under the curve by doing like rectangles or trapezoids or what have you, and then you work your way towards doing the integral. Here, we're doing sort of the opposite. We're approximating the part of doing the summation by saying the integral will give us a good value for that. So I take this, and now my integral is going to look like this. I've also cheated in one more respect. My integral is now over dn, because I'm integrating over the quantum numbers, right? The place where I say I've cheated is I've changed the bottom limit of the integral from 1 to 0. I've done that because in this version I have a standard form, and it makes it a lot easier to evaluate the integral, okay? That isn't going to make much difference. When we get a value for this partition function, it's going to be something on the order of billions. And so adding one more quantum state down there isn't really going to change what we get. So it's worth it for the simplicity, okay? There is a standard form for this integral, which says if I can write the integral this way, I get this nice simple result. In my case, our case here, the nx squared piece, this first one here, that's my x squared. So everything else that's after that in that exponent is going to be a. And that's what's going to let me evaluate my integral. So let's do that. Let's first just write down what a is. A is equal to everything up there except for the n squared. So that's h squared on the top, and it's 8ml squared kb and t all on the bottom, right? That's a. So that's going to let me get my partition function, which says my translational q is now equal to, I get a 1/2 from the integral piece. I get a square root. And inside my square root, I get a pi up here, and I get pi over a, where a is h squared over 8ml squared, Boltzmann constant, and t. I'm going to clean that up some by flipping that stuff up into the top and then doing a little bit more work on it. When I do that, my next one will just say I've got 1/2 times square root of 8 pi ml squared kt all over h squared, because that's the only thing left down there. And in the notes, I rewrote this as square root of 2 pi m kb and t over h squared, and I've pulled the L out of the square root, okay? I know I left the h in there, which I could have also pulled out, I guess, but I didn't. That gives me a version of this that would let me find a value for that translational partition function, right? I need the mass, and I need the box length, and I need a temperature, but everything else there I can just put in numbers for. And we're gonna go ahead and do that now to get an estimate of what this thing might be equal to. So what I'm going to do is I'm going to calculate the value for this for a helium atom moving in a one-dimensional box with a length of 10 centimeters, okay? That's a fairly arbitrary choice of things that I used for that, but I had to pick something, and that's what I picked for this, okay? And so that's what we're going to calculate. Let's go to the equation, which I gave myself a copy of here, right? And so let's just set this up. This is equal to, I get on the top, I get 2 pi, I get a mass, it's a helium atom, so if it was an AMU, it would be 4, and then an AMU is 1.66 times 10 to the minus 27 kilograms. I get Boltzmann's constant, 0.381 times 10 to the minus 23rd. That's in joules per Kelvin. I get the temperature. I'm using 300 Kelvin for the temperature. I don't think I put a temperature on the previous slide, but I should have. On the bottom of this, I have h squared, and then all this is still inside the square root, by the way. All of that is in my square root. And then I'm multiplying that by L. L I gave as 10 centimeters, so I'm going to call that 0.1 meter, because everything in my square root is in SI units. If I do that, I will leave it to you to convince yourselves that the units all disappear. Okay, we have to expand one of the joules in there to take care of the kilograms and the second squareds and then the meter that's on the outside. But all the units should cancel. Partition functions do not have units, right? So if we're calculating one and we end up with the residual unit, we've done something bad someplace. If I evaluate this, my notes tell me that I get a value that's about 2 times 10 to the 9th. Okay, so that's a value of 2 billion. Remember, this partition function tells us the approximate number of significantly populated states. So I do, in fact, have lots of translational states populated. That reinforces the idea that those states are very, very close together. It also means that my approximation of making my summation into an integral was likely just fine, because I clearly do have lots of states occupied, okay? When I go to 3 dimensions, which we'll do in a minute, we'd end up with terms of that magnitude, 3 of them multiplied together. So then we're approaching 10 to the 30th power. So these translational partition functions are in general going to be quite large. We can talk a little bit about how this translational motion contributes to the energy and to the heat capacity, right? My internal energy expression is up top, and so I can just write a version of that that says the translational contribution to the internal energy looks like this. This is a little bit weird here. The constant volume piece turns into constant length because we've gone to 1 dimension here, right? The shift from K up here to R down there, that has to do with making it a per mole value, right? So we could do that either way. If I put Boltzmann's constant down there, then I would be per molecule, and I could do that and then multiply by a number of molecules. That would also be fine. Right? So that gives me an expression for the internal energy. I could, from there, think about doing the heat capacity, right? This part I'm just evaluating what that is, because on this one, I guess I still have it in this form where I've got, the derivative of the log of Q, and that's not that convenient or that explanatory, right? So here, I've substituted in, this is up here, I've got ln Q. Here, this piece, that's the ln and that's the q, right? So that's my ln q in there. If I actually do that derivative, I can very simply pull everything but the t through the derivative, right? And that gets me eventually to a result over here that is just 1/2 RT, right? That says the contribution to the internal energy from translational motion in one direction is just 1/2 RT, and that's going to be energy per mole. Right, because R, remember, has units of joules per Kelvin per mole, so multiply that by T, and I've got joules per mole. Right, that would be my 1-dimensional contribution to the internal energy. Right, that's just like the translational energy for one direction for an ideal gas. If I want to do the heat capacity, all I have to do is remember that the heat capacity is the temperature derivative of the internal energy. Right, and when I do that, I'm clearly just going to get 1/2 R. Right, my heat capacity here, somewhat curiously, again, is written as a heat capacity at constant distance because that box length is now the equivalent of constant volume. Right, so the heat capacity for a 1-dimensional monatomic gas would be 1/2 R. Right, the 1-dimensional monatomic gas is obviously a somewhat hypothetical construct. You could maybe approximate that by having an atom that was free to move along inside a nanotube or something, so it couldn't go anywhere significantly in other directions. But it's still a handy idea for developing the machinery of how we can calculate these things. The last thing we're going to do in this video is going to be to generalize this to 3 dimensions, right? First of all, there's an error in this slide down here. In this version of this row here, those pluses should be multiplied and not added, right? If you add 3 lengths together, you don't get a volume, for example. Right? So I apologize for that. I had that mistake in the slides in the spring in class, and I just totally forgot to fix it and didn't notice when I was prepping to do this. In 3 dimensions, the thing that's good about this is my 3 directions are all independent of one another, right? There's not gonna be any correlation between the X, Y, and Z coordinates if I have just gas molecules flying around in a box, right? There's not a rule that says if I'm at a large value of X, I have to also be at a large value of Y and Z. That wouldn't make any sense. That would say the molecules just all moved around in a crowd somehow, right? So they'll all be separate. So I could, just like I wrote that piece for X, I could write an identical piece for Y and for Z, where at least initially here, I've allowed for the possibility that the lengths are different. So I've given them LX, LY, and LZ. Right? But everything else would be the same. When I multiply those together, all my constants out here, this piece is the same in all 3 terms. So I have 3 instances of that to the 1/2, which gives me all that stuff to the 3/2, right? I multiply the 3 lengths and I get a volume, right? So that gives me the expression for the translational partition function in 3 dimensions, right? And the volume now is in the role that the length of my box was playing before. I can use that to see what the internal energy and the heat capacity have to be, right? The internal energy just goes like this, and if we do that, we know what happens because it's very much the same as what happened with the 1-dimensional case. except now I've got 3 of them, and so my internal energy is now 3/2 RT. Again, you probably have been taught before that the kinetic energy of an ideal gas is 3/2 RT, right? Ideal gases don't have any structure, so they don't rotate and vibrate, and so that's the total energy for an ideal gas, right? The heat capacity is still just the temperature derivative of that expression, and so the heat capacity due to translation is 3/2 R, right? Remember, hopping back to earlier in the video, we had that graph up there where the first plateau, when I said it was just translational motion, that was with the heat capacity sitting at 3/2 R, right? This shows that that makes sense. It is the value we should expect. So that is the heat, that's the total heat capacity for a monatomic gas. If I had helium, neon, argon, whatever, that's just the heat capacity because those can't rotate or vibrate. That same 3/2 R, that will be the translational contribution to the heat capacity for molecules that have more complexity to them, diatomic or polyatomic, meaning we get crazy and go beyond 2-atom molecules, which honestly, in physical chemistry, we spend a lot of time dealing with diatomic molecules because there's a lot we can learn just from them. All right, going forward, in the next video, we will take up the remaining pieces of our partition function. Next come the rotational and vibrational components. Thanks.